Good evening, all of you. So we again meet. This is your mentor Rahul Ghosh. So we meet for the third session of alkyl halides and aryl halides. And so today we'll be dealing with properties, physical properties of alkyl halides first, and then we'll get into chemical properties. So before I begin, let me just log into the lesson also so that I can answer your queries, students. Right. There you go. Good evening, Arun. Good evening, Gopi. Hello, Shyam. Hello, Lakshmi. Right. Hello, Chandramali. Good to see you all. So let's begin today's session. Right. So the deal is again the same. I am discussing the lesson here, the topics here. Anything you feel like asking, you all are free to ask on the spot so that I can answer you, everyone here. Right. Hello, Joel. Good to see all of you. Okay, so first we are going to begin with the physical properties of alkyl halides, right? Okay, now let's first talk about the nature of CX bond. Now, guys, we know that when we deal in your covalent bonds, we have got two types of bonds, right? Polar and non-polar. Now, this polarity or non-polar nature totally depends on what is the electronegativity difference between these two atoms. So right now we have got carbon and the other one is halogens, right? And halogens are known to be highly electronegative, with fluorine leading the pack, right? So basically what we have is carbon as partially electropositive and your halogen as partially electronegative. So in totality there is a polar nature. So we know that these CX bonds are polar in nature. This is something you must have learned last year in your general organic chemistry, GOC. Also you learned about inductive effect, right? Alkyl groups are known to have plus I effect and halogens are known to have minus I effect, right everyone? Hello Akshay, welcome. Okay, so obviously fluorine being most electronegative of the whole group, so CF bond should be most polar while Ci should be least polar in nature, iodine being least electronegative and fluorine being maximum electronegative, a most electronegative element of the periodic table and that group also, right? Okay, so you can see that as we go down the group, what happens ki fluorine, we know that when we go down the group the size of the atom increases. So CF, carbon is what, 2p, and fluorine is also coming from 2p, fluorine, right? Then your chlorine is coming from 3p, bromine is coming from 4p, and iodine is overlapping with carbon with its 5p orbital, right? So we can see that as we go down the group, size automatically increases because you are using higher orbitals, higher your principal level atomic atomic orbital subshells are of the higher order. So automatically the overlap is becoming smaller and smaller, and from valence bond theory you must have learned that more the overlap, stronger the bond, right? So when you go down the group, since the overlap has become quite less, it is easier to break it. So therefore Ci bond can be easily broken in comparison to carbon and fluorine bond. In addition to that, you see that as you have got as you are going down the group, the bond length is increasing because the size is increasing. Carbon is fixed, but size of the halogen is increasing. So therefore automatically the distance from center to center is also increasing, right? So bond length is increasing down the group, but larger the bond length, easier it is to break. So you can see that your bond enthalpies are decreasing while your bond length is increasing. So we can say that from this experimental evidence, we can say that bond length is inversely proportional to bond enthalpy and vice versa, right everyone? So they are inversely proportional. Now, so as bond length increases, your enthalpies decrease, right? Acha. This explains why iodine is the best leaving group in among halogens. Iodine is the best leaving group. Fluorine is the worst leaving group, right? So therefore, note down whenever you will find iodine, because we will be talking about SN1, SN2 mechanisms, iodine will be always treated as your best leaving group. Clear? Among halogens. Okay, now let's talk about their color. In general, if you take a pure bottle of any methyl sorry, not methyl, alkyl halide, you will find that it is totally transparent. So basically, if you talk about the pure compound, there is hardly any color. It's totally transparent. But when you keep it gradually over the time, some sort of coloring appears, right? Especially when it is alkyl bromide or alkyl iodide. Why does this happen? It happens. Hello Srivatsan, welcome, beta. So why it happens? Because when see these bonds, carbon and bromine, carbon and iodine, they can be easily broken with small amount, because they are, you must have seen that their bond enthalpies are not that high. So they may undergo photochemical reactions. These bonds CBr and Ci, they can be influenced by light, and hence they can undergo photochemical reactions, right? So when they are exposed to sunlight or ultraviolet light or heat, they can break. These bonds can break. So and then there will be your free radical mechanism. So there is quite a possibility that, you know, little amount of bromine will be formed, iodine will be formed. So therefore they will appear little violet in color, or they may appear little your brownish orange in color, right? So that is the typical color developed for iodine and bromine, alkyl bromide or alkyl iodide compounds, right? Okay, now let's talk about their melting and boiling points. Now see, when we talk about any substance, it is basically the interaction between two different molecules. How good they are interacting with each other will decide whether they can be, you know, easily taken apart. Easily taken apart means they will be volatile, right? Small amount of heat given to them and they will be vaporized, right? Or if they are holding each other very strongly through various intermolecular forces, then you have to provide them larger amount of heat, so their melting will be higher, their boiling will be also at higher temperature, right? Now the main intermolecular forces that we have studied is your van der Waals force, right? Now along with that, you also have got your hydrogen bonding. So basically आपका hydrogen bonding is now limited. So various intermolecular forces that we can talk about are your van der Waals forces, hydrogen bonding, and your dipole-dipole interaction, which is a part of van der Waals forces only. Right here, van der Waals force here, it mostly means dispersion force. right? Acha. Now hydrogen bonding will be applicable only in case of alkyl fluorides, nothing else, right? Because in hydrogen bonding we have got only fluorine, we have got oxygen, and we have got nitrogen, right? Okay, now yeah, Shivranjani, welcome beta. Right. What happens that, again, van der Waals forces depends on two factors. One, it depends on mass of the molecule, overall mass of the molecule, and also surface area. These are the two things on which it depends. So you see that, if you go down the group, your RF, RCl, RBr, Ri, mass is increasing down the group. So it is quite obvious that if you keep the alkyl group constant and slowly halogens are changing, then your melting point or boiling point will increase from the fluoride towards the iodide, right? And also if you keep the halogen part constant, suppose I am taking chloride only, but then you have got like methyl, ethyl, propyl, butyl. So obviously as the number of carbons will increase, not only the mass is going to increase, your surface area is also going to increase. So either way, bigger carbon chain means means higher van der Waals force, right? Or in case of fluorine you have got higher hydrogen bonding or dipole-dipole interaction. In case of iodine it is much lesser. So these three factors together come into the picture and decide what is the pattern for your both melting points and boiling points, right? So since surface area is important for van der Waals forces, therefore branching or straight chain will also definitely play a role, right? How it is going to be, let's see what happens. I hope this part is definitely clear. Any doubt, please feel free to ask your questions. We'll be more than happy to answer them, right? I wrote in front of it. Okay, the same thing is written here, right? You can see that the lower members are gaseous at room temperature. We discussed that, more the number of carbons or higher the mass, so higher members are liquid in nature and lower members are your gaseous in nature. Exactly the same thing that we talked about in terms of its application, right? Okay, so you can see that every time you change the halogen, right, you are going from chlorides till iodides, keeping the alkyl part same, every time it is increasing in its boiling point. So this is the trend that we will see always, right? You can see it over here also, right? Just because mass of iodine is maximum and mass of fluorine is minimum, right? Okay, so I was talking about branching. Just see here, in case of your N-butyl bromide, it has got higher surface area. It decreases a little if you use non-terminal bromide, and when you have got this tertiary butyl bromide, it condenses a lot. So you can see that it has got maximum surface area, it has got the least surface area, it is almost spherical in nature, and hence your boiling point has also decreased. So you can generalize it like this: boiling point is inversely proportional to branching. You can see that boiling point is inversely proportional to branching, right? I hope this part is completely clear to all of you, right? Okay, let's move on. Now let's talk about density. See, the size increases, but the volume does not increase when you shift from like fluoride to bromide to iodo, right? The volume remains more or less same, but the mass factor is increasing manifold. So you have got kind of similar volume but higher masses. Hence obviously what is density? Mass upon volume. Mass is increasing, volume is not changing by much, so automatically your bromides, iodides, they have got higher densities in comparison to your their corresponding hydrocarbons. So if you take butane and if you take chlorobutane, then obviously chlorobutane has got higher density, right? If you take bromobutane, much higher density, and then of course iodo. So basically what is happening, you are keeping the whole structure similar, simply replacing one hydrogen by either like chlorine, bromine or iodine, and accordingly densities are also increasing. So when you use these haloalkanes, so they will always have higher density with respect to their corresponding hydrocarbons, right? I hope this part is also clear. Okay, let's try to solve this question, right? I'll just call them, say structure 1, structure 2, compound 3 and compound 4. So I'll give all of you 1 minute. Can you answer this simple question as fast as possible? So I'll wait for you. Meanwhile, I'll enjoy my tea a little. Anyone? Akshvel, Maria, Joel, right? Lakshmi, Sham, Shivranjani, Shivatsan. Quickly arrange them in increasing order based on what we just discussed. Anyone? Well, so we see here bromo compounds, right? And this is chloromethane, only one chlorine is there. So obviously with respect to bromine, this one is going to have least mass and hence least boiling point. So what should be the increasing order? So first you should have chloromethane, then bromomethane, because there is only one bromine. So more than this you are going to have one. Dibromo, it has got two, and bromoform has got three bromines because bromoform is CHBr3. So obviously then you have got 4 and at the end you have got 2. So this should be the increasing order of their boiling point, right? Okay, next, again arrange these three based on their increasing boiling points. Again I'll give you all 1 minute. Am I audible? I mean, I hope my streaming is not paused. Okay, my streaming had definitely paused. Yeah, right. Sham, you gave the answer. No, I hope now you know what was the right, what is the right answer. Okay, now here go for the next one, this one. So again let me call it structure compound 1, compound 2 and compound 3. Increasing boiling order, increasing. So let me draw the structure along with them. 1 chloropropane. So you have got something like this. Isopropyl chloride is something like this. 1 chlorobutane. So this everything is chlorine. Look at the number of carbons and the distribution, right? So you can see that 1 chlorobutane has got 4 carbons with chlorine while others have got 3 with chlorine. So automatically this should be having highest mass among the 3, right? So 3 should be 3 should have highest boiling point. So at the end you should have got 3. Now among 1 and 2, 2 is branched while 1 is linear, right? So we know that boiling point is inversely proportional to branching. So therefore you should have got 2, right, followed by 1, followed by 3. So this should be the order of your increasing boiling point, right? Okay, I'll move on. Next comes the concept of solubility. Now solubility first of all depends on a very simple thing, and you must have some heard about it in your solution chapter also, that like dissolves like, right? So if I may write it, right? Now haloalkanes are mostly kind of non-polar. They are not, I mean the overall molecule, not the CX bond, that is polar, all right, but still the overall molecule if you talk about is kind of non-polar, because bigger the alkyl group, more the non-polar nature, right? So if I'll say that, say 1 chlorobutane is less polar than 1 chloropropane, which is less polar than 1 chloroethane, and so on, isn't it? So therefore you will see that the initial members like 1 carbon, 2 carbon, methyl, ethyl, they are slightly very sparingly soluble, but the higher you go they become almost insoluble in water, right? For the simple reason that when you add these new molecules to water, the energy needed by these molecules to break apart the hydrogen bonding is much lesser. I mean they possess much lesser energy with which they can break apart the hydrogen bonding. Since they are unsuccessful in that, so therefore their solubility is highly influenced, so they are hardly able to break them apart. But if you talk about organic solvents, then you will find that these alkyl halides are pretty comfortable dissolving in organic solvents. Why this happens? This happens because there the energy needed to break apart the organic solvent molecules is exactly what possessed by them. So therefore the intermingling is much easier in organic solvents in comparison to your aqueous solvent, right? I hope this part is clear, very much clear, right? Okay, so this is the compilation of what I just discussed, right? So they are simply unable to overcome the hydrogen bonding interaction, so it is very difficult for them. And when they are added, when these alkyl halides are added, the energy provided is very less, the energy released is very less, and hence they are unable to break apart the hydrogen bonding. That's where the problem lies, and the ultimate result is the solubility is extremely low, right? Almost sparing, or down the group it becomes almost insoluble. Two separate layers can be seen very clearly, right? Okay. And when you add them in organic solvents, then there is not much of problem, right? Because the attraction is very similar. That's what we talked about. The attraction among them organic solvent and among them is very similar. So therefore, you know, they are quite comfortable in getting dissolving in organic solvent. So here lies the concept of your like dissolves like, right? Okay. So I hope this much part is pretty clear to all of you, right? Okay, so we are done with the physical properties of your alkyl halides. Now we are going to move on to the chemical properties of alkyl halides. Just like your initial preparation, we have got here three broad categories under which we divide the alkyl halides, all the chemical reactions of alkyl halides. One is their nucleophilic substitution reaction. Second is going to be their elimination reaction, and at the end their reaction with highly reactive metals, right? So these are the three broad categories that we are going to deal in. So one is your nucleophilic substitution reaction, which we abbreviate as SN, nucleophilic substitution. Elimination reactions or E reactions, they are again of like E1, E2, base catalyzed, acid catalyzed. They are also in, they can be bifurcated in the various parts. So I'll be taking extra class, special class, especially for JEE and NEET aspirants who are where we are going to discuss in detail some applications of your SN and how that can be used to solve various questions directly asked from JEE or NEET, right? Acha. And then of course we are going to do reactions with metals towards the end. So today let's focus more on nucleophilic substitution reaction, right? Okay, so basically what is a nucleophile? A nucleophile is a group of atoms or an atom with a negative charge, and I mean it can be an anion, or if it is neutral then it has got extra lone pair from where it can attack. Like ammonia has got a lone pair, water molecule has got a lone pair, alcohol molecule has got a lone pair. So these all can attack with their lone pairs, and hence they can be termed as neutral nucleophiles. Nevertheless, the symbol that we use is Nu negative, right? So this is the symbol for nucleophile. So basically what is happening, a nucleophile is attacking your alkyl halide, and this will substitute the halogen atom. So halogen atom is becoming here the leaving group. It becomes here the leaving group. And if you remember, the best leaving group among halogens is iodide, right? So it will attack here and get itself attached over here. So how the way it attaches it and the way we get the product in optical sense is what we will see what happens in SN1 or SN2, first order or second order, right? Fine. Any doubt till now? You please, you can write it over there. I'll be happy to answer that, right? So basically the idea is that, you know, if you keep on changing your nucleophile, right, you have got Rx, you attack with different nucleophiles and you are going to get various products over here, right? So with product, let me have little water product. Okay, so that means we had Rx, you attacked it with OH minus, right, anion, you attacked with H2O, neutral nucleophile, you will end up having end up replacing X by OH. Similarly, if you do it with RO minus, you are getting ether, right? This will lead to something called Williamson synthesis. We'll study in next chapter in detail. ठीक है. NaI you have already studied, right? Finkelstein reaction, remember? You could have AgF also, Schwarz reaction, same thing, fluoride is replacing it. Now if you deal this with ammonia, you get primary amine. Again, when RNS2 will react, you will get secondary amine. Again, the same thing will attack another RX, you will get tertiary amine, right? So primary amine, then secondary amine, then tertiary amine. These are your Hoffman ammonolysis reactions. Hoffman's ammonolysis reactions. You will study about them in preparation of amines. They are amines are being prepared here, primary, secondary and tertiary. Ammonolysis is what you get. Then you have got again this silver salt, right? Here you have got this as the, from here you get this as the nucleophile, which will give you ester. Fine. We studied this in when iodine was there, we did study about this also. Iodide, alkyl iodide was there, right? Acha. Then if you want to reduce an alkyl halide, you treat this with lithium aluminium hydride. Hydrogen, your hydride is actually replacing this, so H minus rather will come over here and you are getting RH, right? Of course hydrocarbon is obtained. Then at the end you have got this metal, you have got this here, and this is the carboanion that you are getting with the help of this, and it will replace it. For example, if you take Grignard reagent, then this can happen, or Wood's reaction also, this is going to be helpful. That we'll talk about later. But these are the basic nucleophiles that you have got, which can replace here. Another one can be like your sodium acetylide, right? So if you remove this, you have got then H C triple bond C, the acetylide anion, and you are going to get a higher alkyne, CH, right? And also it's a step up, you are getting alkyne. There's a step up reaction. Why? Because you are adding 2 new carbons over here, right? So this is very helpful to us. Now there are something called ambident nucleophiles. There's something called ambident nucleophiles. What are ambident nucleophiles? These are the nucleophiles where you can have more than one atom for attacking on the substrate, right? So the nucleophiles have got more than one atom from where they can attack, but please remember it is only one atom at a time. It's not that more than one atom is going to attack, right? No. So either atom A or atom B will attack at any given point of time, and hence the outputs are different. So one good example is potassium cyanide and silver cyanide. Now see here, as an inorganic reagent, they are both cyanides, right? But the nucleophilic part, you see, in case of potassium cyanide, carbon has got the negative charge, right? But in case of silver cyanide, nitrogen has got the lone pair from where it can do the attacking. So ultimately the final product in case of potassium cyanide, what you get is RCN, but in case of your isocyanide, you get RNC, RCN, and here you get RNC. So isocyanide you get with when you have got silver, and otherwise you have got this thing, right? Acha. Now you can see that they can always interchange like this, and hence they can change the site of attack, right? Okay, now one thing is why this happens like this. Like in the first case, potassium carbon bond is purely ionic, right? So obviously potassium, by staying nearby, ensures that the negative charge resides on carbon atom from where it can do the attack, right? Potassium ensures that carbon is going to do the attack, I mean, by staying nearby it. But in case of silver cyanide, this bond is partially covalent bond. This bond is partially covalent bond, or you can say that covalent character of silver carbon bond is much higher than that of potassium carbon bond. So automatically, nitrogen being most electronegative, it pulls electron from carbon, which in turn forms silver. So this is partially negative and this part is partially positive to start with, right? So the attack is naturally going to take place from nitrogen. So when nitrogen slowly attaches itself to the new alkyl group, silver carbon bond slowly breaks apart and you end up getting the isocyanide instead of cyanide as the previous case. So I hope you guys are clear how this ambident nature is imparted on certain nucleophiles. The same thing is true with another group, KNO2, potassium nitrite and silver nitrite. So here NO2 also acts as an ambident group. How? Let's see. See, KNO2 and AgNO2. In case of KNO2, the attack is from oxygen, while negative charge resides here. While in case of your silver nitrate, again the same thing. Now it's from the other side and it attacks from the lone pair and hence you get this thing, right? So again, ultimately what happens, it is the partner metal atom which helps the anion rearrange itself and behave as an ambident group, right? So it's the linkage that affects, right? I hope this part is completely clear to all of you, right? Okay, let's do certain question. So again, I'll leave it on all of you for 1 minute. Just go through them and try to answer quickly based on what we have seen, how they are supposed to react. Any answers quickly? These are very simple questions that have been put forward. Okay. Any answers? I'll simply refresh it. So what we get here is, since you are, what is this? This is with acetone, heat, NaI you are dealing with. This is your halogen exchange reaction, right? Your Finkelstein reaction. So basically chlorine will be replaced by iodide as the nucleophile, right? So you should therefore get, so you have got 1 chloropropane, so you should get 1 iodopropane. Fine. Okay, then in the next case you have got sodium hydroxide. That means the nucleophile is OH minus. Here the nucleophile was I minus. So OH minus is going to attack this carbon and make it lose bromide as the leaving group. Here iodide was the leaving group, right? So you should get, this is what, 2 bromo butane. You should get butane to all, right? Butane to all. And of course your Br minus will be the leaving group. Yes, Cl minus was the leaving group. Right. Now you have got aqueous ethanol as a solvent and you are dealing with potassium cyanide. So potassium cyanide means carbon is the attacking atom, right? Because cyanide is an ambident nucleophile. So in case of KCN, you get bromine replaced by cyanide, right? So basically what we have is this, right? So from 2 carbon, now you have got 3 carbons. So it can be used as step up reaction. It can be used as step up reaction, right? On the other hand, if you had AgCN, silver cyanide, then the output would have been NC, that is isocyanide. And very clearly you can see that I'm giving you an additional information. If you reduce this, so what you are going to get is this. So this is your secondary amine. So this is one of the method of preparing secondary amines, right? This was your step up reaction and this was conversion to secondary amine. So these are small things which you can keep on picking while doing these kind of questions, which is going to help you in subsequent chapters, because ultimately a chemical property, a chemical reaction in one chapter will be preparation of another compound in some other chapter. So basically you are repeating reactions. You should always look for these kind of subtle hints, and these will reinstate and reinforce the concepts in you, right? So this will make your organic chemistry quite easier if you do it in this fashion. Okay, now we are going to talk about mechanisms. Two mechanisms, one is your SN1 and SN2. So let's first talk about SN2 mechanism, that is nucleophilic reactions, nucleophilic substitution reaction of second order. 2 here means second order, right? And what is second order as per chemical kinetics? It means involvement of 2 reactants in the rate determining step. So ultimately it is a rate determining step that is going to decide the fate of kinetics over here. So if it is if it is a second order reaction, then in the rate determining step it must be 2 reactants. So you can see that you started with 2 reactants here. So what is happening here? OH minus being a nucleophile, it attacks the carbon containing chlorine. But from where is it coming? It is coming from the rear end. It is coming from the rear end. So it is coming from exactly the opposite direction where your chlorine is pointed. So it is going to attack from the rear end. Why rear end? Because this whole mechanism is driven by steric hindrance. That means your nucleophile will always come from a point where the crowding is least, right? So it is driven by steric hindrance, right? So what happens? You get and it is your RDS, rate determining step. So what is happening? It is attaching itself. It is trying to attach itself, and in the meanwhile, see, carbon chlorine bond is getting loose. You can say that this is one single plane. Okay, there is one single plane. So while from one side OH minus is coming up, from the other side Cl wants to leave the system, or you can say it is making the Cl leave the system. So ultimately what is going to happen? It will become a proper bond while this will go out, right? Acha, in the same time you can see that when OH becomes a complete bond, then it will force these 3 hydrogens to move on the other side. See here, so this was the bond, all them have moved on the other side. Here this is the plane, sorry, not the bond, plane. here initially they were in this direction, now they are in that direction. So this is what we call bond inversion, right? This is what we call bond inversion. So you can see that whenever there is going to be your SN2 mechanism, it will always involve bond inversion, right? Okay. So you can see that this is your rate determining step, right? It is following your second order kinetics, because concentration of both the reactants plays an important role over here. So if you decrease concentration of the nucleophile, rate of reaction will decrease, and if you decrease or increase concentration of the substrate, the same thing is going to happen. So it depends on both of them together, hence second order kinetics, right? Achha, so basically as we talked about, this is like inversion, bond is getting inverted. So initially it was in this direction, and there is, as soon as this nucleophile is entering here, it is flattening up, right? So it is the nucleophile, and you have got the other bonds over here. So I hope this is clear, right? The bonds are here, there's the nucleophile. So when this is incoming nucleophile is here, then slowly this bond is flattening, and when this part leaves, then it fixes like this, and they will slowly bend on the other direction. So initially they were in this direction, now they are in this direction. It just looks like this umbrella. So if you take your umbrella on a very windy day, right, so the moment you go out, there's quite a chance that your umbrella is going to get inverted like this. So it will turn in other direction, right? Okay. So since we talked about your steric hindrance condition, so we know that whenever there is a very large group of atoms or a bigger group present, they are going to hinder you sterically, or they are going to stop you from entering. So therefore, if you have got like tertiary alkyl, so it is definitely going to give you like 3 bulky groups, like 3 methyls are there, 1 methyl, 1 ethyl, and other combinations are quite possible. So they are going to stop or slow down the incoming nucleophile. So nucleophiles, when they want to undergo SN2 mechanism, they do not prefer tertiary. Secondary is still kind of fine, but primary is their favorite. Why? Because in primary, even if one alkyl group is there, the other 2 are hydrogens, and then they are going to provide least of the hindrance, and attachment becomes much easier, right? So therefore this is the steric effect or inhibiting effect, it stops, and hence you can see that order of reactivity is always primary greater than secondary greater than tertiary in case of SN2. So I hope this part is completely clear, right? Any more doubts? Any doubts from any one of you? Nope. Okay, so this is very much clear in this graphic. You can see that it is trying to attack from here. So if you take ethyl as unit 1, so then if it is methyl, then it is 30 times faster. See, presence of just one alkyl group and other 2 are hydrogens, you can show that it has slowed it down 30 times, right? And if you go for 2 alkyl groups over there, then it is 0.02 times. That means it decreases with respect to alkyl 50 times smaller, right? And when you have got tertiary, then it tends to become 0. So hardly we see formation of any compound with the help of tertiary and SN2 mechanism. So for tertiary, SN2 mechanism is almost nil, right? Okay. Now we get into SN1 mechanism. Now SN1 mechanism is like it is not what is apparently seen. Now, what I mean is that you have got 2 reactants, but when we check the reaction path, reaction mechanism, we find that the whole mechanism is independent of the presence of nucleophile. That means concentration of nucleophile has no influence on SN1 mechanism. It is possible only if this whole reaction takes place in more than one step, and nucleophile concentration or nucleophiles are not part of what? They are not part of, yes, anyone? They are not part of the rate determining step, right? So rate determining step only depends on concentration of the alkyl halide. So it has to be multi-step reaction, right? Acha. So you can see that we in the last case we saw that with tertiary butyl there was no SN2 mechanism, but still we are getting this. That means, and that too does here it is happening with the steric hindrance. So hence, since steric hindrance is there, there must be some other mechanism by which it is taking place. Okay, so let's try to understand what happens. So in the first step, you see this is breaking apart, right? And you are getting the carbocation, and since it's a tertiary carbocation, so it's quite stable in nature. You get a stable tertiary cation, and since there is a bond breaking going on, a bond is breaking here, it requires energy. It's an endothermic process, right? So it is a slow process. So out of the two processes, this is slow, right? And hence this is your rate determining step. This is clearly your rate determining step. So therefore, if you write the rate is going to be K into your, in this case, CH3 thrice right. So this is your rate determining step. So the next step is kind of electrostatic attraction. So a cation is getting attracted towards an anion, they are forming a bond, and this step is quite faster. So fast steps are never part of your rate determining steps, right? So first one is reversible and slow, the second one is quite fast and hardly any back reaction takes place. So it's a one step go, right? Okay, so this is how your mechanism takes place. Now since there is formation of carbocation in the first step, so it is quite obvious that your order is now going to follow exactly the stability of carbocations, which is tertiary greater than secondary greater than primary greater than methyl carbocation. So that is how your SN1 reaction has got highest preference for tertiary and least preference for primary, right? But that's what we are discussing here also, and they are definitely they are provided when we provide polar solvents. This mechanism is seen quite repetitively because carbocations are more stable in polar solvents in comparison to your non-polar carbocations. So as we discussed about, higher the stability of the carbocation, which is your tertiary, more we see formation of more we see SN1 mechanism. With lower stability, we have seen that with SN2 your primary is preferred, with SN1 your tertiary is preferred. In fact, if there is allylic or benzylic carbocations, they are preferred more than tertiary carbocations, right? So order will be benzylic, somewhat similar allylic because of their resonance stabilization, followed by tertiary, secondary, primary, and then methyl carbocation. Vinyl will always come at the end, right? Okay, so as I discussed, your allylic and benzylic halides have got a higher carbocation stability, and hence they are better than your tertiary carbocations. So you can see that in allylic carbocation there is clear resonance, right? So this can again come back over here. So this charge, this positive charge is dispersed, and more the dispersion, more the number of resonance structures, more the stability, right? And in case of benzylic, we have got 4, and the repeat will be again the same. So therefore we have got 5 structures in totality. 4 main structures we are seeing over here, right? So they give better SN1 reactions. Okay, so now basically what are the overall factors on which this influence of SN1 and SN2 depends. So we are just discussing the heads of the factors. In detail we'll discuss in next class. So one, structure of the substrate, as we discussed. If they are primary, then what is preferred. If they are tertiary, then what thing is preferred. So for primary we get SN1, for secondary we get for primary we get SN2, and for tertiary we get SN1, right? So that's why structure of substrate, we'll discuss that in detail in next class. Concentration and reactivity of the nucleophile. If it is SN1, then it is independent of the nucleophilicity of what is there for the nucleophile group. Like, but if it is SN2, then of course concentration and reactivity of your nucleophile is very important, because not all nucleophiles behave in similar fashion, right? Effective solvent is definitely there. Polar, non-polar. For if it is SN1, then effect of solvent is very important, and of course nature of leaving group. Let us quickly get into this also. As we discussed, structure, you can see that tertiary is preferred by SN1 and your primary is preferred by SN2. So it is the structure, right? Achha, concentration, you can see that SN1 is independent. It does not depend on your nature of nucleophile at all. But in case of SN2, you can see that if water's value is 1 unit, if it is HS minus, it rises by 1,25,000 times. So therefore different nucleophile, different rate of reactions for SN2. This is very important point, when you have to compare which one is a better nucleophile to attack and undergo a particular reaction. So these things will definitely help you out in deciding that, right? Okay. Effect of solvent, as we discussed, your SN1 mechanism definitely depends on polarity of the solvent also. Higher the polarity, more the stability of the carbocations, and hence this is quite important for us, right? And if it is SN2, then non-polar solvents are always preferred, in which this is very important solvent, takes place in many reactions, right? Okay, and as far as your nature of halogens are concerned, we talked about this in the beginning of the session only, that doesn't matter whether it is SN1 or SN2, iodine is always the best leaving group because of its bigger size. Best leaving group, right? While this one is the this one has got the strongest bond, and hence it is the worst leaving group, right? So quickly, a question: among these two, which one is going to prefer SN2? You can see this is what? This is secondary, this is primary, right? So SN2 is preferred by by secondary over primary, so it should be this. Now here you have got one iodo alkane, chloroalkane, so doesn't matter whether it is SN2 or SN1, iodo will definitely be faster. It's a better leaving group, so it should be like this, right? Now you have to pray it for SN1. This is what? There's primary, there's secondary, so, right? SN2 we talked about, sorry, I took it for SN1. SN1 primary is preferred, so this is wrong. Right, for primary, for SN2 this is going to take place. I thought for SN1, my apologies. In the second one we have got SN1, that's why it immediately stuck. That last one was SN2. So here we have got primary, here you have got secondary. So here this is better than this, but we have to talk among these four, right? So here we have got, this is also primary, here this is tertiary. So basically the fight is between these two, because other two are self decided. So this one is your structure 4. The structure 4, let's say this is structure 1, 3, and say this is 4. So you can see that 4 is going to be for SN1, right? 4 is going to take place fastest, followed by your secondary, right? So structure 2 will come, and out of these two, this has got more stability, see, more inductive effect, and hence this primary carbocation is going to be more stable than this iso carbocation is going to be more stable than this N-butyl one. So therefore you should have got like tertiary followed by primary, the first one, sorry, right? I hope this part is also clear. Now what we have, the order we have to be following compounds in SN1 reactions, So you have got here benzylic carbocation, you have got 2 phenyl carbocations over here, right? This bromine is attached to this carbon actually, and here you have got this 1, 2, 3 and 4. Okay, so here you have got 1 phenyl carbocation, I mean 1 phenyl group and 1 methyl group. Here you have got, see, this carbon has got 1 phenyl, 1 methyl, another phenyl, and then this bromine. So this is tertiary, right? This tertiary, this one is 1 hydrogen is there, hence this secondary, this is primary, all of them are benzylic, right? So that's not the point. You have got this as again secondary, right? This is quite interesting question. So you have got 1, you have got 2, you have got 3, and you have got structure 4. So if you see, the one with only one phenyl group has should be the lowest in rank, least number of resonance structures, right? So this should be 1 here. Okay, we have to decide for 2, 3 and 4. You can see that there is secondary, and these also, yeah, but here you have got only 1 phenyl in 3 also, and other 2 you have got 2 phenyl groups. So therefore, but here you have got secondary one, so it should be structure 3. Agreed? And what you have is here 2 methyl groups, here I've got two phenyl groups, here also there are 2 phenyl groups, but 1 methyl group is also here, right? So therefore you should have got, because of this methyl group, it's tertiary, secondary, so therefore structure 2 here, and strongest is structure 4. So I hope this order is clear to all of you. Just look at the structures, draw them, and you will understand that why this order should be there, right? So with this we come to the end of today's session. Next we are going to have some extra sessions, I mean for understanding of your SN1 and SN2 and their application, mainly for JEE level questions, NEET level questions. It will be a very interesting session. I am looking forward to it. Hopefully you all will also enjoy. So with this, it's goodbye from your mentor Rahul Ghosh, sir. So we see you in the next session. Have a good day. Bye.